Arka. If you are Arka, I don't know because a while ago Dr. Soumitra was talking on you from your account. And on the other hand, I would like to say that I'm not a professor. Yeah. Okay. On that note, let's start the presentation. So firstly, let me share my screen quickly with you guys. Please let me know if you are able to see my screen.
Yes, yes, sir.
Thank you very much. So the topic of my presentation today is advanced analytics in process metallurgy. I'm Dr. Amiy Srivastava, and I'm currently a process engineering specialist in STELCO Incorporated, Canada. This company is situated in Ontario, Hamilton, and this is kind of a very old company. Like as we have a very old company, Tata Steel, like that was opened in 1907. Similarly, this company is also very, very old. Like it was opened in 1800s, kind of end of 1800s. Okay, so but this topic, the topics which I'm going to cover, I'm not going to talk about what I'm currently doing in Stelco. Rather, I'm going to cover what I have done in my PhD and postdoc fellowship when I was in University of Toronto. So let's start the first slide. Start. Okay, so since although this conference is going to be related to machine learning and advanced analytics and data analysis, but by heart and by profession, we are process metallurgists, right? And since we are material scientists and or metallurgical engineer, so we should know that where we can apply that machine learning, the concept of machine learning. Once we know that, we can we can model our process in order to get multifold benefits. But before that, we should know what is process metallurgy. So process metallurgy is concerned with, I hope most of the people in this call know about the process, what is process metallurgy, but still, I should start with this. So process metallurgy is concerned with the extraction of metal for their ores and refining the metal. People might say that, okay, process metallurgy is only related to steel making and hot processes, but after steel making, when we cast our liquid steel, that time also process metallurgy comes into the picture. Apart from that, like when the casting ends, and that casting can be of any type, whether it is continuous casting or batch casting or die casting or I would say belt casting, any type of casting that will come under process. And the study of all these processes would be called process metallurgy. And after we have the near net shape, like the casting structure, we take that to rolling mill and we generally deal over there with mechanical metallurgy and physical metallurgy. So here I'm going to talk about like process metallurgy, which includes the principle of chemical reaction, heat and mass transfer, thermodynamics, fluid dynamics, etc. And these days, in order to develop advanced fields of process metallurgy, people are using machine learning. So gradually, we will start with process metallurgy and the idea of metallurgical engineering, and then we will gradually move to machine learning. So let's move on to the next slide. So, since we are going to talk about a process, and I understand that many students over here are from their undergrad, maybe third year or fourth year of Bachelor of Technology. So, I wanted to explain a little bit about one process. And here you can see this is the picture of a continuous caster. So, on top of that, you can see ladle. This ladle is basically coming from secondary steel making. So I believe that all you guys have idea, all of you have an idea about how steel is made. So firstly, like some people have direct reduced iron furnace, or we call it DRI shaft furnace, mid-rex, core-rex, and all. And some people have blast furnace. We get hot metal from the blast furnace, and it goes to the primary steel making station. There we can have electric arc furnace or we can have basic oxygen furnace. Like very old people, like those who were working in Steel Authority of India Limited or ArcelorMittal Tufasco, or they were working in Stelco, so they might know the process of open hearth as well. But that process is completely extinct these days, like obsolete. No, so from the primary steel making section, we get primary steel, and that primary steel doesn't have any alloy. And as we know, because of our knowledge in mechanical metallurgy and physical metallurgy, that in order to achieve standard properties in steel, we have to add a lot of alloying elements. And for adding the alloying elements, we have to take our liquid steel from primary steel making section to the secondary steel making section. And in the secondary steel making, we add alloy, we increase the temperature, maintain the temperature, and we whatever we get, that is called secondary steel. And that secondary steel is collected in a ladle. Ladle is kind of a bucket, and that ladle comes to this continuous caster. In all, most of the, in I would say 97% steel plants these days are having continuous casting machine. So here you can say ladle is taken from the steel making plant and then like secondary steel making station, and then it is kept on this turret. This turret can rotate like 360-degree, and and then after that we connect that ladle with a shroud. Shroud is basically nothing but a pipe made of refractory, and that liquid steel is transferred from this ladle to the tun dish. And then this tundish is used as a buffer between this ladle and the mold. Mold is situated just below the tundish, you can see here. And mold is the place where solidification takes place. Why are we making the steel? Because we need to make big structures, we need to make car body, we need to make plates for different applications. So we have to solidify the steel. And because we cannot sell, jokes apart, but we cannot sell liquid steel to any customer, right? So for converting the liquid steel into solid steel, we have to solidify this thing. And for the solidification process, we have to use continuous casting mold, and these are the mold. So in this image it is called crystallizer, but it is called mold. And after the in the mold, solidification process is taking place by means of internal cooling. And then as soon as it comes out of the mold, like the shell is already solidified, and that shell is further solidified, like shell thickness is increased when we impinge some water spray on the surface of the strand. And when it comes, like we it faces the bending and unbending, and after that it gets straight, and after that we cut this strand based on our length requirement. And because some company has the capability of transporting the billets which cannot be longer than 12 meters, so that's why we have to cut it 12 meters, or maybe that is the maximum length. And also that length is determined by the size of the plate, like which we are going to roll from that strand. So that is the ballpark idea of the process. But I believe most of you have already an idea about, whoever is attending this class, maybe having this idea about this process. Now let's move on to the next slide. So, but when we are doing this casting process, a lot of problems can occur. And if these problems are not occurring, so we will not be hired, right? We are hired to solve these problems. What can be those problems? So there can be some solidification related defect. So what are those defects? Those are called center crack, longitudinal body cracks, edge cracks, mold oscillation marks. These type of problems are observed by several casting engineers and metallurgists. Second problem can be multi-phase related defect, because we not only have liquid steel, but also we have inclusion, and some people also inject argon gas into the mold. And so because of that reason, we have different phases. We have gases, we have liquid steel. So that's why we call it multi-phase related defect. And the defects which are originated because of these multi-phase flows are sometimes called blister, sliver, and and sliver is basically nothing but inclusion is transferred to the shell of the continuous casting strand by means of bubble transportation. We will talk more about it if we get a chance. Then we have mechanical related defect as well. For example, you have seen in the diagram that casting structure, like some people have 2R radius continuous caster. So that caster is basically bent from two different radius. So when this bending and unbending is taking place, that time some transverse cracks are formed, and those are because of the hot ductility. Those happens because of the hot ductility trough. So these are the problems, and process engineers and process metallurgists, they have to deal with these problems. Now let's see what is the importance of process metallurgist. Yeah, so when we talk about the importance of any engineer or any professional, we always try to convert that in terms of money. how much money that guy is saving or how much money that guy is making. That is very important. If you are not making any money, so there is no use of your employment over there. So, like in the fast-paced environment these days, you can be hired, you can be fired as soon as you will be hired. So that's the thing. So why process metallurgists are important? Let's see. So what happened? Like we get an order from the customer, and we have to, and this is our responsibility that whatever material, whatever order we have get, we have to supply the material, supply the end product to the customer on time. Like we cannot delay this thing, and in full. Like we have to supply it full in like if we have got the order of 1,000 tons, so it is not possible that we just supply them 950 tons or maybe 900 tons. It is not possible, but it happens sometimes, or maybe many like those processes which are not properly controlled. In those plants, it has been seen that people are not able to make good quality material in one go. So what happened? Like a lot of problems can happen. So first of all, like inspection cost can increase because when you have a hunch that your material is not that good, so you have to invest a lot of money to people and who will go and inspect the final product. Because suppose you are selling some plate to government of India, or I would say DRDO or some sophisticated customers, and if you are having a lot of cracks or a lot of defects in your plate, so it would be very difficult for you to convince them so that they can buy that type of plate. They cannot buy it because they are bounded by the standards, and those standards are quite stringent. Second thing is fear of undersized plate production is also there, because if we have to suppose we get some crack at the edges. So what we have to do, like we have to crop that edge from the sides. And if it is cropped and our order width is certain and we have cropped it more than the certain order limit, so that plate is basically wastage. So undersized problem can occur over there. And then we have to recycle the material because we are generating more and more scrap, and then we have to recycle that material in order to get the same order which we could not supply because of having a lot of defects on that product. So if we are recycling, so recycling is basically nothing but we are adding that scrap into our steel making process. And you know that, like, if we add that scrap in our BOF, so BOF is responsible for producing a lot of carbon monoxide and carbon dioxide gases. Carbon monoxide is converted at high temperature at stack, but still, a lot of carbon footprints are increasing for the same order. So, like, environment-wise, also, it is not a good idea. Then wastage of conversion cost, like we have already produced some material, we have invested some money to produce, like it is called conversion cost. Like suppose some steel is coming from continuous casting and then it is going to rolling mill. So we have invested around maybe 5,000 rupees or 10,000 rupees to convert that from liquid steel into the solid steel and roll it. And then we identify this product is waste, like defective. So whatever conversion cost we have put over there, that is wasted. So that is also a huge loss to the company. Carbon emission per ton will increase. We have already talked about it because we are producing more defective material, waste material. Then fear of defect exposure at the customer. This is a big problem. Suppose you sell some wire rod to the customer, and customer finds that your wire rod is having a lot of cracks. So, like your reputation will be on stake that time, like, and your reputation will be deteriorated, I would say, because customer will find out, okay, this company is having a lot of defects, so it is risky to buy anything from them, because like it is not possible to inspect 100%. We only do the scientific sampling. We only check our samples like after 5 coils, after five batch of products or something like that. We cannot do 100% checking. It is like there are some sophisticated products which we have to check 100%, but most of the cheap products we cannot check test 100%. So customer will always think that, okay, this guy is having a lot of defects, so it is always possible that some of the products which he has left and which he has not inspected, that might be having some defects, and that will create problem in my at my end. And I have already talked about on time in full policy. And these days, in order to increase the cash flow, companies always want to increase the to adhere to the policy of on time in full, because that will help them in transportation. they get their money like from the customer as quickly as possible, and then they can invest that money in other ventures so that they can earn more money. So cash flow is very important. You like if there is no liquidity in your money, it is a big problem. But if you are producing defective material, so liquidity will be there would be a liquidity crunch in that case. And then delay in delivery, because when we get an order from the customer, we sign that we will deliver this material on this particular date. And if we are not able to provide that material to that customer on that particular date, so we have to provide some penalty, or like customer can claim against that. And we have seen that in all other many services, like in flight booking also, you get some money paid if your flight is getting delayed. So that type of thing is possible. So all these problems are causing money. And who can save this money? A process metallurgist. Okay, so that's why so whenever we are studying something, we should know what is the importance of that subject matter, and that will help us to study more about that thing. Okay, so that's how I wanted to just tell you that how important it is. Let's move on to the next slide. Yeah, but what are the tools of process metallurgist? Yeah, I am process metallurgist, and I can say like I can solve the problem. I can solve the like I can reduce delays. I can delay in terms of call. I can improve the quality. I can do a lot of things. But how I will do that? That is another thing, because there are many limitations over there in a steel plant. First of all, is most of the steel plants, like many steel plants, are very old. Like those have been set up long time ago, and that time, like our computer knowledge and our electronic knowledge, that was not that robust, right? So we did not have many sensors. And second problem is like steel making is a volume business. Like we produce one heat of 250 tons. If there is a problem in making one heat, so we are losing 250 tons. 1 ton is causing maybe 50,000 rupees. So 50,000 rupees 1 ton. So like in one mistake, and we are losing 50,000 into 250 tons. So that much money we are losing. So it is like, and the cost to company of one defect would be huge, kind of. So that's why, like in rolling, it would be less. I was calculating for the steel making, but still for rolling also it is like vital, like it is huge. So we have to solve. We have to. So process metallurgists are having some tools, and they can use those tools to identify the process, whether the process is under control or it is kind of out of control. If process is out of control, so process metallurgist has a responsibility to to make that process under control once again, so that they are not producing more and more defective material. So what are those tools? Those tools are basically models. Different type of models can be used to assess a process. Yeah, one limitation I did not tell you, like if anybody of you would like to go to work in a steel plant, they will realize that it is a high temperature process, and it is complex process also. High temperature means we are talking about 1600 degrees Celsius, 1550 degrees Celsius, like that, because that is melting temperature of steel alloy. Like there is a range of that, the melting temperatures. So so if we are dealing with that temperature, that time we cannot see anything. Everything is quick. We cannot go close to the process. If you go close to the process, you are basically risking your life, and that's why a lot of safety aspects are followed these days in all the steel plants all over the world. But still, so tell me, how will you solve a problem if you are not allowed to go there to see? And even if you go there, you won't see many things, because all those processes are opaque. So most of the work, such work is done based on basically sensor data analysis. Like these days, because of the advancement in electronics and electrical engineering, we are we have we have put a lot of sensors, different type of sensors in our processes. Like mold, we have different thermal sensors, thermocouples. A lot of temperature measurement is there, a lot of things, fume measurement is there, level measurements are there. So a lot of things are, so we can just analyze that data. That is one thing. And second thing, like if we don't know anything about that process from scratch, we have to develop some physical or mathematical model. And like long back, like when we did not have these facilities, like data analysis facility was not there, and computational models were not there, physical models were only so physical models were there, but data-driven model and computational models were not there. So that time people were using mechanism models. So those mechanical models were based on basically small experiments, some application of statistics and empirical correlations were used. For example, I published a paper 2, 3 years ago, and we developed an equation for dephosphorylation index. So we already 99 equations have been developed before, and we developed I think 101th equation, and that was more robust because the prediction through that equation for the dephosphorylation was more accurate than all those equations developed previously. So why our correlation was better? Because we applied data-driven approach, and previous scientists they applied empirical equations and statistical models they applied. So those were based on the combination of some equations and some empirical data. So that type of thing they did. And so second thing is we talk about the data-driven model. So this is kind of a hot topic these days. Like if you have knowledge of machine learning, so you can go to anywhere in all the industry 4.0 is coming up not slowly, like I would say very fast. And all the companies are doing some projects related to machine learning, deep learning. So those data-driven and those processes which are more related to such sensors, sensory data, and which are more complex. So people have found that if they use data-driven type of analysis, so that would be easy for them to crack what is happening over there, like to identify the problem exactly at very less time. So not only for the process metallurgy thing, but also for maintenance people are using. I am in contact with 3, 4 companies I have hired in my company, and they will be working on that from a machine learning point of view. Now, third thing is physical model. What is physical model? This is pretty interesting. So suppose we have a continuous caster in our plant. Yeah, okay, and we want to understand how fluid dynamics is taking place in a ton dish. Like I showed you in previous image that liquid steel is transferred from ladle to the ton dish. When it is transferred to Tundis is basically liquid, and kinematic viscosity of liquid steel at around 1600 degrees Celsius is equal to the kinematic viscosity of water, right? So liquid steel will also flow, and we have to identify the flow structure in the Tundish. And if we can identify the flow structure, we can easily identify or we can predict what will be the quality of the solidifying steel or solidifying strand in terms of inclusion. So that type of thing we can do. So what we generally do, we know our the dimensions of our continuous caster which is there in the plant, and we make a mimic like physical model of that plant in our lab, and we perform water modeling or different simulating liquid we can use, and then we see what exactly happening in case of water, and then we can extrapolate if this particular thing is happening, flow dynamics, flow behavior, if this type of flow behavior is there in water, so same thing would be happening in case of steel. And then we can do some hit and trial, we can do some changes in our plant, we can do some studies like in terms of flow, like flow rates or design of the equipment associated in with that model, and we can see that okay, if this problem is happening a lot more time over there in our model, so if we change the design, if we change the flow rates, then this problem will not occur, and then we can apply so same flow rates or same process parameter in the real plant, and we would expect that this problem will not occur second time, or the frequency of that problem will reduce significantly. So that there are some limitations also for the physical model, but still these for liquid steel flow identification, it is or for multi-phase also it is quite useful these days. And the fourth option is computational model. What is computational model? This is basically based on computational fluid dynamics and heat equation. So we know you might have heard, like, I don't believe that it is there in fourth year curriculum. Like, I'm talking about Navier-Stokes equation, or maybe in heat transfer it might have been taught, but I don't remember it during my time it was there or not. So there are some flow equations like Navier momentum equation, Navier-Stokes equation. So we solve that computationally. So we make a flow domain. Like suppose we have a tundish. Tundish has a dimension like shape and size. We make a 3D diagram of that tundish in our computer, right? On our computer, and then we make the mesh like grid on that particular geometry. And after that, at each node, we calculate the solution of that Navier-Stokes equation. And after getting the solution, we can get the value of pressure, temperature, velocity of the fluid element at each and every nodal point. And if we couple the energy equation with this, we can identify the temperature also over there. If we couple the species transport equation, we can identify what is happening, like if any reaction is taking place, what is happening over there. So that type of thing also is possible these days. You might have heard ANSYS Fluent software, which has been used these days by researchers to identify the flow structure or to study the flow behavior of different things. Like this software is not only used in steel making and iron making, but also it is used in aerodynamics and several heat transfer calculations, like development of heat sink. These things also over there also it is used. Like for for uh, developing the optimum design of a car, that software is also used. So that is another part that is called computational model. So like a process metallurgist should have the knowledge of all these four branches, and then he can contribute to reduce those problems which we were discussing before talking about this slide. But there is a limitation of computational model. What is the limitation? Like it needs very high computing power of the computer. Like if you want to do something on your laptop, like you will not be able to resolve the complex flows. And even if you do something, I don't think so. Those are going to be used in your real life application. So you need to have, like these days, people use supercomputer for resolving these issues. I hope, like if India do something about it, like I hope it will be extended to quantum computing also. Like I have heard recently, like China and USA, they are working like very hard on like in terms of quantum computing. So if those things will come, so these problems can be solved very quickly. And maybe that time that physical modeling and mechanism models will be obsolete and nobody will be using that. But for now, we have to use those two models as well because we have computational. There are some limitations of computational model. If we talk about the limitations of data driven model, so those are there because sometimes what happens, we get a lot of false data in the real plant situation. If you go, you will find that some of the outliers are there, so sometimes it becomes difficult to identify what is outlier and what is not an outlier. And also sometimes some sensors are not working, so you lose a lot of data, and if you lose some data, so your results will be biased and you cannot rely on them. So that is the limitation. So each and every model has some limitation. So I won't say that it is a gospel and like we can solve like 100% of the problems using these four models, but sometimes it can be solved, sometimes it can be just reduced, not solved. Now let's move on to the next slide. So this is kind of a, so we have to use combination of, like in order to solve one problem, like for example, if we are getting blister defect in continuous casting slab, so in order to solve that problem, we have to apply different type of models. It is not possible that we use just only one model and we can solve the problem because these problems are quite complex, right? So I have made the flow diagram over there. So you can see here basically process modeling of multi-phase flow in steel making and casting. So it can be studied using three different models. Like, and here I have given the sign AND gate. So AND gate means like there is no OR here. So you have to use all three, and then only you can solve these problems. Sometimes you can use two to solve the problem, but it is recommended to look at all these three type of models to solve a big problem. If we talk about the fluid dynamics based problem, so and if we talk about multi-phase issues, so in the multi-phase we can have different type of phases like gas, slag, metal. There can a lot many interactions can take place. If you are going to study for the fluid dynamics based model, basically computational, it is also called computational model. If you study all these three interactions in one go, it would be very, very complex. And computational power which is required would be like very high. So it would be very difficult for you to simulate these three interactions in one go. So what people generally do, they separate, they take only two interactions in one time, like gas and metal interaction, only slag and metal interaction, or slag or gas interaction. And similarly, these two interactions can be studied by physical modeling, and physical models can be of different type. Like as I told you, that kinematic viscosity of liquid steel at 1600 degrees Celsius is equal to that of water. So people make water model, but I found in my research, like when I was in U of T, that no, sorry, yeah, when I was doing my postdoc fellowship, I found that only just for studying the multi-phase flow, just water model will not work because water has limited surface tension values and limited viscosity values, limited density values, water at different temperatures. But so that may not be equivalent to the density, surface tension, and viscosity value of real liquid steel. And when we talk about the multi-phase flows, it means we are talking about gas metal interaction or maybe slag metal interaction. So if two phases are there, so one phase is kind of a matrix, and second phase is the dispersed phase, and that dispersed phase can be affected by these properties like density, viscosity, and other, like one other property was there, surface tension. So if we just study multi-phase flow using water models, so it would be difficult for us to be unbiased, to be because maybe that data is not correct. So I realized that I should change the simulating liquids. I should understand the effect of different viscosities, different properties of the liquid on the size and shape of the dispersed phase. In my case, dispersed phase was bubble. We will talk more about it later. And if I have a class tomorrow also, I will talk about like how I will talk more about this thing. And the second thing is CFD based mathematical modeling. We have already talked about it that we ANSYS Fluent is used for that, or people are using OpenFOAM these days because that is free. You don't need to buy license for that. But here is the catch: like when you implement heat equation over there, so that time it is called non-isothermal model. Like you because you are considering temperature as well. But if you are not, if you are just after if you are just interested in looking at the flow behavior of liquid steel or water. So that time you are not implementing any energy equation over there, and that time it would be called isothermal model. But again, I would say we are just simplifying the model more and more, and that will not be as equivalent as what we are seeing really in our plants. So if we are not making the model as it is, then we are not solving the problem basically. So that is the thing. So that's why we should use non-isothermal model. Yeah. So let's move on to the next slide. So in session one, I'm going to talk about physical modeling, imaging, and image processing with machine learning application. And I believe Dr. Soumitra can talk about it. Can tell me. I do have another session tomorrow also, Dr. Dinda, right?
Yes. Tomorrow morning from
Yeah,
same
yeah. So
time.
tomorrow I will talk about, I will touch data-driven modeling and some examples of advanced machine learning technique. So let's move on to the physical modeling thing. And today we'll talk about image processing and imaging and image processing using machine learning techniques and basic methods. Okay. So, quick introduction to physical modeling. Because why again trying to tell you this thing, because imaging and image processing comes into the picture when we do the physical modeling. Because in the data-driven modeling, we don't need physical modeling, and in other models also, we don't need image processing and imaging. For physical modeling, only we need it. So, steel making and casting process involve high temperature and rapid flow dynamics. These processes are not transparent, and visual observations are impossible due to high temperature. Processes are not even accessible. I told you about it. Then replication of such processes in lab can only help to understand them. Physical modeling is one way of replicating these complex processes. This is not completely true, because if your process is too complex, I don't think that physical model will be able to. As soon as you increase the complexity of the process, I think you will not be able to solve it using physical modeling. So this sentence is partially true, I would say. Then what are the components of the physical modeling? So physical, we need to decide what stimulating liquid we are going to take. Like as I told you, whether should we take water or should we take liquid metal like gallium, indium, tin alloy, or we should take another liquid metal which smelting point is little bit higher. Like I was talking about gallium, indium, tin alloy, the speciality of this metal is like at room temperature it is liquid. So if you can see the bubble through this metal, you can identify what is happening at very high temperature, at very high density and viscosity, as well as surface tension. What is your bubble size or what is your dispersed phase size that you can identify? But yeah, that metal was quite inexpensive stuff. And yeah, I ordered that like 60 kg when I was at U of T, but that was very expensive. And the second part is like experimental setup, including piping systems and pumps. So yeah, so this is another thing. So you need to mimic your real continuous caster. So once you are mimicking, once you are making like a model, so you need to have a knowledge how to make the piping system, how which pump should be used, and like which equipment should be used so that it cannot be corroded by the water and or by the liquid metal, and those the like pump material should not be reactive. A lot of calculations you have to perform. On the other hand, you have to perform a lot of symmetrical calculation like geometrical symmetry, and then you have to decide on your flow rates, and for that you have to perform this what it is called, another geometry is called, I'm like, yeah, I'm skipping, like yeah, I'm not able to recall the name. Yeah, but we use fraud number similarity criteria for that. Yeah, so like dynamic similarity criteria we have to use. Then only we can decide, okay, because if we don't use the correct flow rates and if we don't use the correct piping system in our physical model, so it would not be mimicking our real continuous casting process. And then all the results would be wrong. So you keep on doing the experiments, but you won't get any results. So we have to take care of this thing. So kind of some knowledge of mechanical engineering is required, kind of. Then observation equipment is also very playing very important role. Like for example, like how are you going to observe? Like are you going to observe the conductivity of water when you inject any external dye, or you are going to see the color of the water? What you are going to, or you just want to see the images? What you want to do? So based on that, you have to buy observation equipment. After that, whenever you have observed, so that data should be recorded somewhere. So you have to buy some good quality computers and which can handle that many data points. And once you have that data, you need to analyze that data. And for that, you need to have image processing. So, sorry, you need to have data analysis software. If you are taking images, so you need to have image processing software, or you should be having a knowledge of coding like Python, or so how are you going to write programs which can analyze your image quickly? So and yeah, because time is also critical. So because of these components, physical modeling becomes expensive. It becomes like more expensive than data-driven model, and I would say sometimes it's just fluent also. Yeah, if we remove the element of using supercomputer in case of computational model, then I think that would be way cheaper than a physical model. But since like these days we have access to computer like supercomputers, so that is also not a difficult part. But itself, ANSYS Fluent license is quite expensive. That's why people are using open form. Let's move on to the next slide. So again, this was the example of our metallurgical process. I have already talked about it. And but keep in mind, because I'm going to talk about this part. This is called a tundish. And this tundish is basically used as a buffer between ladle and the continuous casting mold. If we don't have this tundish, then liquid steel will be transferred to the mold directly, and we won't have any area where we can control the flow, where we can do some additions, or where we can whatever we want to do, we can do that thing in this tundish. So this is kind of an essential part of whole continuous casting process. And second thing is mold, and we will talk about these two things in the coming lecture slides. Okay, let's move on to the next slide. Okay, so now I'm going to give you an example of first physical model, and now it will give you a clear-cut idea. So firstly, you can see here what I wanted to see in this. So we have this is kind of a 2D diagram. I made this thing, like, sorry for my bad art. So you can see here we have a ladle, and on top of that we have a ladle slab, right? And in here we have tundage, and on top of that we have in this we have liquid steel, and on top of that we have tundage slag. So what is happening when ladle slag can be entrapped, can enter uh, can enter the tundage liquid steel by means of vortex formation, and vortex can be of different types. You might have seen, like, in your wash basin, when the liquid level, like water level, goes down. So that time you might have seen a vortex formation. So one that type of vortex formation is there in our ladle also, and because of that vortex formation, some slag can be transported to the tundage. And but that slag is having, like, that can create a lot of problems, because wherever that slag is there in between the steel, and when you are going to roll it, like, it since it is brittle, so it will be broken off, or the steel, like, lot of issues can happen related to steel cleanliness. Apart from that, other thing is, maybe you can discard some steel. You may not be using that steel, but apart from that, what can happen, that slag can remove the top layer of tundish slag, right? And we engineer tundish slag, and for the particular type of steel, we engineer or we make particular type of tundish slag. Like, we define the chemical composition of tundish slag, and like, for the sophisticated products, we have to use that type of slag. And in this case, what can happen, that ladle slag can hit the turbo stop, like bottom of the tundish, and it can move upward, and it can interact with the tundish slag, and it can remove the layer of tundish slag in here. So this was one of my PhD topics. And you can see here I did some physical modeling here, and I develop a physical model, and then after that I took some images here, like, so now you can see, like, how I took different oil for ladder slag, and I took different oil for the tundish slag, and I gave different colors to that, and then you can see how that oil is introduced, and how this interface is moving to the right, and how it is changing the chemical composition of the tundish slag. And in this condition, when lot of mixing has taken place, that time the property of, uh, like, the function of tundish slag, which allows it to protect the liquid steel, is basically gone. So tundish slag will not be able to function well if this situation happens. So you can see this type of phenomena can happen. So one open eye can be formed, like, and the liquid steel can be exposed. You see that red oil is removed, and in here, like, when this is introduced, like when the ladder slag is introduced, that open eye was increased, like, it was extended. Upon further introduction of ladder slag, like, it was extended further, and in here, so, like, all the tundish slag was removed. And if tundish slag was removed, and new slag was taking the place of the old slag, so that is basically we are losing the protection of steel, and which is something we don't want. But all these things can, like, any model can be made out of this when we have very good quality images of this thing. Do you think, like, it is like we can measure the size of the droplet over here? I don't think so. Why? Because this is transparent. So, like, we can do it manually, but manually it is not allowed. Why? Because we have to process many images. Like, we have to process, if we do it manually, like, it will take 2 years to finish just one small analysis. So how much time I will take to finish my PhD? Maybe 10 years, or maybe more than that. So you can see this is the front view of that image. So physical modeling of liquid steel flow in tonnage. So this was one example of physical model. Now second one is, you see, this is a continuous casting mold. So what happens, like, liquid steel from tonnage is transported to the mold, and over there we inject. So when liquid steel is transferred to the mold, it carries a lot of inclusions also along with this. and that those inclusions can be like stick to the inner surface of this SEN, like submerged entry nozzle, and that is that is called clogging, SEN clogging. We call it the phenomena of SEN clogging. And once that happens, like flow can be changed, and if that flow can be changed, the structure of liquid steel flow, that will also be changed, and we are producing bad coils all the time. So what happened, like in order to avoid this clogging phenomena, we inject argon gas. Why argon? Because argon is inert gas and it will not react with steel. And over there, like steel is super refined, so we cannot introduce any other gas other than carbon because there is no chance of reversing that process. Suppose if we inject nitrogen, like in many processes, nitrogen is used as a coolant. But if we inject nitrogen over here, so steel nitrogen ppm of the steel will become very high. And these days, like customer wants us to supply like 50 ppm or 40 ppm nitrogen, not beyond that. So we cannot inject nitrogen. All other gases, like we cannot inject oxygen because oxygen will oxidize iron. It will convert that into FeO and then Fe2O3, Fe3O4, and so on. If we inject hydrogen, like hydrogen entrapment can happen, like and that would be having different hydrogen related granular hydrogen related defects. So we can only inject organ. But when we inject organ, that produces bubbles. You have seen that when you inject gas into water, that produces bubbles. And what happens that those bubbles, there are some bigger bubbles and some smaller bubbles. Bigger bubbles can go up right away, and they can make this type of open eye. Basically, they are removing the mold slag layer. So we have a mold slag layer also, which protect our steel. But these bubbles can expose that liquid steel. It can open up that area. And once it is open up, what happened? Like a lot of oxygen can go from outside into the steel, and that can create some exogenous inclusions. And you know, inclusions are not good for steel, for any steel. So, and some bubbles are very small in number, like small in size and and those bubbles they don't have appropriate buoyancy, so they cannot flow. They cannot be flowed up to the top surface, and they move to the side wall of the mold over here. And over there, solidification is already taking place, so they are basically entrapped at the secondary dendritic arm spacing (HDAS). Some bubbles are also entrapped at primary dendritic arm spacing, and so those are creating a lot of edge cracks, and those problems are called like blister and sliver defects or pencil pipe defects can be observed in the pencil, and those that type of steel is not acceptable by the customer at all. So what happened to solve? So to solve this problem, we need to know how bubbles are produced at different gas flow rate, different liquid flow rate, and how that bubble size is impacted. So we will talk more about it tomorrow. But you can see here, this is the real, this is the picture of real plant, and we cannot see anything over here. Everything is closed. So how will we solve this problem if we cannot see anything? So we have to make a mimic model in our lab. So in U of T, we were having a full scale water model, and we were doing a lot of experiments when Dr. Dinda was there as a postdoc fellow with me. So he was also doing a lot of experiments in a full scale model. So these are the reasons we have to use physical model. So crux is that all physical models require state-of-the-art imaging and image processing. Yeah. So in order to resolve the size of these bubbles, number of these bubbles, we have to use state-of-the-art image processing and imaging technique. Now I'm going to talk about imaging. So you can see from the flow of the presentation that gradually I'm moving towards machine learning. This model is also running. Yeah. So this kind of a bench scale model, it is a very small model, but you can see small bubbles. And one thing you can identify how fast these bubbles are moving. So, and if we want to find out the velocity of these bubbles, so it might be triggering, like since all you guys are engineers, so you might be thinking that we have to use high speed cameras. Then only we can identify the speed of one bubble or each bubble. You can see how fast it is, like these bubbles. So this is kind of a top view, but some bubbles we can see. We will see more, like in the next slide, we will see more. Okay, let's move on to the next slide. So advanced image processing techniques and their application in physical modeling of continuous casting process. So why image analysis is required? Real life experience. Let's see some videos because maybe some people are like sleeping. So let's wake them up. So you can see. So this is kind of a busy square. I don't know which country is this, but I hope this is like China or maybe I don't know. And you can see we want to know what is the speed of the car. So we were like, like where from we have got that video. So that machine learning like data scientist, he applied some advanced techniques like maybe in YOLO or something, and he is like calculating the speed of the car. We can also identify whether it is a car or it is like whether it is a car or it is a truck and what is the speed. So for the surveillance purpose, it is kind of a very useful tool. What can be the next application of machine of image processing? So these are the basically cells. So like all those biomedical scientists. So they are using these cells and they want to know the size and number of these cells. Like for example, cancer cells. They want to see the growth of the cancer cells. So they can also use image processing to find out. You can see some small particles are there, and now they have labeled it. They have counted. Okay, in this area we have these many cells, and then they can also identify what are the size of these cells. Okay, 1 month ago that size was this much. Now in just 1 month that size was increased significantly. So like it is, these are basically growing cell, and it can cause like a detrimental effect on the health of the patient. So there also this machine image processing technique can be used. On the other hand, if we take the example of a plant, you can see this is a slab coming out of the reheating furnace, or maybe after 2 3 rolling passes, and we can identify from the like if the corners or and the edges of this slab are colder or black in color, it means the temperature has gone down over there significantly. It means temperature has gone down. It means the what it is called, the plasticity or ductility of that area have also been gone down, and because of that now a lot of cracks can be produced if we roll it further. So that type of thing we can observe, and we can have a lot of subsurface and surface cracks. And if we have these images, we can just analyze these images and we can identify, okay, this slab should not be rolled further because whatever time we are spending in rolling this slab, we are basically producing bad quality material, and all that electricity, conversion cost, water will be used to roll that. That will go in vain. That will be wasted. In the second image, you can see like this is the measurement of zonal temperature in a reheating furnace. So in the reheating furnace, we gradually increase the temperature of a bloom. This is kind of a bloom, round bloom, and we cannot increase the temperature very fast. So we have to do it gradually. But we need to know at what zone, like what was the temperature at, like temperature zone wise temperature we need to measure. So what we do, we apply a thermal camera over there, and then we analyze those images and we identify, okay, this should be the temperature of this zone, this should be the temperature of second zone, and also we can identify the surface temperature of that bloom also, and that will help us to identify the rolling temperature, because we know that we have to take the temperature at the austenitic region, but too much high, like if the temperature is too much high, so basically we are increasing the size of prior austenitic grain size, and which is not recommended because that can produce lower strength material later. So that is another thing we can identify. So you can see, and also we can find out the temperature from end to end. Like at this end, this is the temperature. At the center, we have this particular temperature, and at the tail end of the bloom, we have this temperature. So what happens? Like in general, we have to increase the temperature of the tail end because tail end spend more time in the mill. If it spends more time in the mill, why? Because like it like that rolling process is taking place gradually. So tail end is in the atmosphere for more time. So in some mills, some covers or troughs are not available. The troughs are available, but heat-saving covers are not available. So in that case, a lot of temperature is lost at the from the tail of the bloom. So in that case, what we have to do, we have to increase the temperature so that when that part of the bloom is getting rolled, that time temperature will not go down, and that will not affect the like roll separating forces. And if that would happen, so like if that otherwise, what will happen? Like roll may be broken, or roll may be like current may increase, gearbox can be broken, so a lot of problems can happen. So we have to maintain the temperature of this bloom. In the second, and that temperature can be measured through thermography. Now, in the third image, you can see this is the ladle, and ladle is getting transferred from one station to other station. And if we see a black spot, or a red spot in this ladle, we can say, okay, maybe the refractories have been deteriorated significantly, and because of that, a lot of heat transfer is taking place from the liquid steel, like to the ladle wall, and that we can see. So ladle is going to puncture, and if a ladle gets puncture, and if somebody is standing near that ladle, so that guy or that person can be exposed to the liquid steel, and that is kind of dead, like he will die for sure. So, so thermographies are used to see the health of the refractory of a ladle, and we can identify, okay, so this ladle is of having high temperature, this ladle is having lower temperature, and we can also perform end-to-end thermal modeling, and we can identify the superheat. We can calculate the superheat for the best quality material. Fourth image you can see, this is basically for the condition monitoring purpose. We in the steel plant or in the chemical refinery, you might have seen like hot liquids or hot temperatures or steams are transferred from one place to another place. So if there is any problem at the joint, for example, if weld joint is having any problem or something, so that area will be emitting a lot of heat, and that heat um, can be identified through thermal imaging. And after image processing of those thermal images, we can identify that, okay, that area is kind of a problem, and we have to solve this issue. And that all these things are coming under condition monitoring and asset reliability. So you can see like how imaging is useful, and one can build his career on just imaging and image processing only throughout his life, and they can earn a lot of money. How it is important. Now, second thing is like imaging in process modeling. So I have already shown you before, like this this image I have already shown you that we are seeing some open eye formation, and we can measure the size of the open eye, and we can identify, okay, how much oxygen can enter into the mold through this open eye. This is one thing. Second thing is like you can see the bubble formation. Sorry. Yeah, you can see the bubble formation here in a mode, and then you can identify, you can take the size of the bubbles. You can measure the size of the bubble, velocity of these bubbles. This video you have already seen like how ladle slag is introduced into the tundish. This image is also very interesting. Like these days, like spray technology is like very hot these days. Like people are using sprays for many different purposes. So we need to see, like for powder processing also, sprays are used. So you can see that how you can identify the size of the droplets using imaging, and those droplets will help you to reduce like, because you have to produce certain size of the powder, and that size will be dependent upon the size of the droplet over here, because droplet and liquid metal interaction will determine the final size of the powder. But if you have very small droplets, or if you have such droplets which are not according to your optimization, then you will not be having certain like appropriate size of the size distribution of the powder, and your material will be rejected. So you can identify the size of the droplets, like these are water droplets, and then you can measure the droplet size distribution, and you can change the flow rates, and you can change the design of the nozzle, and you can achieve the like the required droplet size distribution. So this is also required. And here you can see, like this is from this diagram, you can see like how we can measure the size of the ladder slag droplet over here. Okay, let's move on to the next. I wanted to give you a flavor of physical model. So, like this physical model we have developed when I was at U of T. Dr. Dinda was also there with me. So here you can see like how we developed the physical model. So this is a complex physical model. We use different type of pumps, air pumps, and we use different type of flow meters. And the design was also very critical. We have to make sure that it is completely imitating the casting speed because in the mold region casting speed is quite slow, so flow behavior should also be imitating we cannot withdraw water at very high flow rate, otherwise we will not be able to imitate because in reality water is not coming out from here, basically strand is coming out and the strand speed is very low, like so we have to make in such a way so that uh, like we can imitate the exact casting speeds over here. So that's why we made three chambered model here. And then we took this is kind of a field of view and we took the images to see the bubbles. So this is kind of a like schematic of physical models we have developed. There are many different type of physical models available, like people have made. You can go through research papers and you can learn about the physical modeling thing. Now we talk about the image processing. Okay, now you can see like we have talked about where we use image processing. We have talked about the imaging thing. We will talk a little bit more about imaging to give you a deeper idea about this thing. But let's talk about image processing first. So there are two methods of image processing. One is basic method. Second one is advanced method. I call it that way because I found it that way. The basic method is basically you don't need to use machine learning, but that depends on on one limitation. Your image quality should be very good. If your image quality is not that good, then you will not be able to use basic method. So then you have to use machine learning. So provide and better results if image quality is very good. Processing through several steps such as image conditioning, background subtraction. We'll talk about all these steps later. And it is a time-taking process, but yeah, we can do batch processing to analyze our images using basic method. But one limitation is there: if your system is that very complex, if your velocity of the bubbles or any disperse phase is very high, that time it is very difficult to use basic methods. And for what purposes it can be used? Like for object counting. Suppose you take an image and you have 1,000 objects. So it is easy to count those 1,000 objects from that image. That can be done. For that you don't need to go to machine learning. For object motion sensing, if you are able to, if you are having good high speed, high resolution camera, so you can identify the velocity of the moving object very easily using basic method. You don't need to go to machine learning. Yeah, but I would say if the flow is the dispersed phase is quite dense, then sometimes it is difficult. It is very difficult to identify object motion through basic methods. And object size estimation can also be done using basic method only. But again, I would say your image quality should be very good. Now let's talk about the advanced method. So in the advanced method, we use machine learning and provide satisfactory results even if image quality is not very good. Like you can get very good idea and very fast, also relatively quicker than basic methods. Processing through low number of steps, such as the area classification by the use of classifier. So like when you use basic method, that time you have to apply many different methods, many different steps. But if you do like apply machine learning, that time you don't need to apply many different steps to do so. So that way it is good. But yeah, it needs computational power, and for the computational power, you have to buy good quality of desktop or sometimes supercomputing also may be used. But so, yeah, but it is less likely to be used for our purpose, for process metallurgy purpose. Then for object identification and classification, this is the best method. For multiple object motion sensing with a dense population. Yeah, this is one thing. Like object motion sensing could be possible with basic method also, but suppose if dense population of of that object is there, like suppose instead of if 1,000 bubbles are moving, okay, you can identify the velocity of that bubble, like average velocity easily you can identify. But when those 1,000 bubbles, like when each bubbles are crossing each other, so what will happen? As soon as it crosses, like one bubble will cross the path of the another bubble, old data will be removed when we use basic method. So in that case, we cannot use basic method. We have to use advanced methods. And for object size estimation in poor quality images also, we can use this thing. So we generally use convolutional neural network. This is kind of a very famous thing in the field of process modeling, I would say, both for process metallurgy and chemical engineering research. So people are using CNN. What softwares people are using these days? Like for basic processes, you can use ImageJ. It is like continuously improving because scientists who are developing ImageJ, they are including new and new libraries every day, I would say. And so sometimes you can get, but still you have to use some algorithm and you have to learn ImageJ. But Fiji is the advanced, like this is the logo of Fiji. So Fiji is the advanced version of ImageJ. So a lot of things which you have to install in case of ImageJ. Fiji is already in Fiji it is already inbuilt. So you just need to update your Fiji and all those libraries are there, most updated ones. So you don't need to search. MATLAB, we already know that people use MATLAB. Everybody uses MATLAB and OpenCV Python, like one library, like one version of OpenCV Python, like called OpenCV that deals with image processing. That so ImageJ, Fiji, and OpenCV Pythons are free version. MATLAB we have to pay like for getting the software. Okay. So requirement for acceptable images for basic images. Because I was talking about all the time, I was talking about good image quality, good image quality. So what is good image quality? What we call a good image quality? Okay. So what is happening here? Suppose if you are trying to resolve multi-phase flows. So in multi-phase flow, you should be having at least two phases. So let's take as I told you that scientists have resolved like they study two phase interaction and then they move to three phases interaction because if they right away start to study the three phase interaction process will become too complex and they will end up doing nothing and they will waste a lot of time. So that's why people generally want to do start with two phase simulation. So in two phase simulation, two phase multi phase studies, what happened like we have one disperse phase and one matrix. So in order to get good images or easy image processing using basic methods, we should be having a foreground and a background. So if we have a foreground, like a I will talk about foreground and background in the later slide. Yeah, but image quality should be very good. We should be having clear cut background and clear cut foreground. Then only basic image processing methods can solve this issue. Even some advanced techniques also cannot resolve clearly if you don't have a distinct foreground and background. What happens? Suppose you are making some physical model, and in the physical model, bubble the color of the bubbles is also white, and your background is also white. So when you take the picture, you are seeing everything is white. So if these are not distinct, like bubble is also white and your background is also white, so then you are not able to any like your eyes even would not be able to identify whether it over there we have a bubble or we have like nothing over there, like because the bubbles are transparent and there is no color in the bubble, right? So that's why that distinction is quite play an important role. That distinction play an important role. Then interface clarity. Like we need to know that okay, disperse phase has ended up here, and after that matrix has started. If interface is not clear, so it means images are of not good resolution, and we will not be able to get the correct size of the particular disperse phase. Maybe velocity you can identify, but if you have many bubble, I would say if your flow domain is densely populated, in that case, you need to have good resolution, no matter what type of image analysis technique you are using, whether it is basic or advanced. Okay, proper frame rate is also important for speed calculation because bubbles are moving very fast. Or and if you don't have proper camera, if you don't have proper high speed camera, which can get you to 1,000 or maybe 4,000 FPS frame per second, then you will not be able to identify the speed of those fast moving disperse phases. So proper frame rate is also important. Now, one by one, we will take all these three things. So you can see, I was talking about, see here, like if you talk about this bubble is also white, like this bubble is also white here. Near the light, it is more white. So even our naked eyes, like through visual inspection, we cannot see this bubble. Like we have an idea, but we cannot see this bubble. So it is difficult for image processing technique, which is kind of man-made technique. It is difficult for that also to identify this bubble. So, and you see the how fast it is. So if you don't have high-speed camera, you will not be able to see anything. So another picture is here. This is little bit better, and I made this thing using my iPhone. Yeah, so I use uh, the slow motion uh, feature of my iPhone, and I saw I could reduce the size, sorry, speed of the bubbles, but still we see a lot of black. Like this bubble is black, and like this is foreground. This bubble is foreground called foreground, and background is also black. So both are black. In here, both were white, but in here, both are black. So it is very difficult for an image processing technique to identify the size of this bubble because interfaces are not clearly distinct. We cannot know. We don't know. We know that something shiny is over there, but we don't know where is the interface. So what we implemented in our analysis, we started doing shadowgraphy because the previous PhD student before me, like he was applying shadowgraphy technique for resolving his spray, high speed spray, and he suggested me to use shadowgraphy in our case. So what we did basically, this was our model, and behind this model we put a continuous illuminating source over there, and in front of that we applied like high speed imaging camera. So see, like naked eyes, you cannot see anything, but you will when you see the results, like this is the result of. So now, what is the beauty of this video? Like we can see like foreground and the background is clearly distinguishable. We can see all the bubbles clearly without any problem, and we can see like all the things are clearly visible. And since we had a good quality high speed camera, so we could measure the speed of the bubbles clearly. So let's run this video and this video together. So this is the real speed and this is high speed imaging, and this is acceptable. If we have this slow, we can like using the basic method, we can measure the velocity of the bubbles. Okay, so let's move on to the next slide. Okay, so I'm going to talk about the interface thing, like if we have clear interfaces or not. So for that, we have to decide the correct depth of field when we are taking the images. So what is depth of field? The examination of depth of field is important to identify whether the captured bubble are sharp enough to provide size and shape. So this research is from CSIRO Australia. So in their image, we found a lot of blur images were there. So these are basically bubbles, but their DOI was not correct. So because of that, we are not able to see this bubble. So basically, what is happening over here, like foreground is getting equivalent to the background, and image processing techniques are not able to distinguish between foreground and backgrounds. We are not able to see anything. And why it happened? Because their depth of field was lower than the mold thickness. So this is our mold thickness, for example. So depth of field should be higher than the mold thickness, then only we can see the clear quality image. And these are the formulae. Depth of field is calculated for the camera setup. I don't want to go into the details of this thing. If you want to understand, if you want to learn more about it, it is already given in my paper. So my paper is given here. Like this was published in MedTrans B in 2022. So there I talked about the importance of depth of field. Now let's move on to the next slide. What is the importance of frame rate? So here we have 50 frame per second. Here we have 100 frame per second, and here we have 1000 frame of second. And this is showing like what type of high speed camera we use. So I'm going to play all three videos, and then you can compare. Like here, bubbles are quite fast. 50 or for basic image processing techniques, if you want to find out the velocity of each bubble, this video is okay. 50 FPS is okay. 100 FPS is like you see slower bubbles, and these are the 1000 FPS bubbles, like very slow. Bubbles are moving very slow. So you can see like each and every phenomena, how bubbles are coalescing with each other, and how bubbles are like bubbles are breaking, like two or three bubbles are produced from one bubble. So those phenomena you can see if you have 1000 FPS uh, camera, like high, if your camera has that capability. In our camera, we could go up to 4000 FPS, I believe, 4000 or maybe 2700, something like that. Okay, now I'm going to talk about what is image. What is the what basics of image processing I will teach, I will tell, and then I will talk about what is an image. So what is image is basically nothing but a two-dimensional a two-dimensional image is basically, or a digital image is basically nothing but a matrix. A digital image is defined as a two-dimensional function fxy. This is fxy, where x and y are spatial coordinates, and the amplitude of f at any pair of coordinate x, y is called the intensity. So you can see this is x, y, and these are basically pixels. F00 is pixel situated in this position. F01 is the pixel situated in this situation. F02 is another pixel situated in this situation. And these F00 are basically representing the intensity of that pixel. The minimum intensity of the pixel is 0, and the maximum intensity of a pixel is 255. So if you see 0 anywhere, like not F00, F00 is just showing the position. But if you see 0, if 0 is written anywhere, it means it is a white pixel. If it is 255, if you see anywhere, it is basically a black pixel. And any number in between is your gray image that you can see. Okay. Now let's move on to the next slide. Here, like whatever I was discussing, like here you can see this is our image, and this image is basically pixel, like how the pixels are how this is converted into the pixels. And here we have, like, this is the liberty of a statue, and this image, if you go closer to this image, how you can pixelate this thing in terms of intensity. Now let's move on to the steps of basic image processing techniques. So we got these many bubble images. This is one bubble image, the second bubble image. So yeah, and we have to perform some operations in order to achieve the final image. Like we can identify the size of the bubbles when we have binary images only. So we have to convert our real images into binary images. So these are the methods where we use what we perform in order to get our binary image. Firstly, we have to crop the area of interest. Then we do some background subtraction. After that, we applied band pass filter. Then we did some image contrast or image sharpen. And after that, and you can see some white spots over there. These are coming because of the light reflected from the surface of the bubble. And we have to fill this hole because this is a 2D image. So for that, we apply we apply fill holes. And some bubbles are like very close to each other, like they are joined. So but we need to have the size of individual bubbles, so we have to watershed the group of the bubbles, and then we can identify the and after that we apply analyze particle, and we can find out the size of the bubbles. That was the basic image processing. But what happens, sometimes we get this type of image quality, and Dr. Dinda should be very much familiar with this image. Okay. Yeah, so and this is very poor quality image, I would call, because you see the background is also not that good. So it is very difficult to segment this image. For that, we have to use machine learning techniques. So image segmentation is very difficult due to no distinct boundary. You see, somewhere it is like this is gray and the foreground is gray and background is also gray. But that was our limitation. Our physical model was that time, it was of that type. We cannot get any image better than this. So that was our limitation. So uneven background was there in that. Then and bubbles were also densely dispersed throughout the flow domain. So a lot of noises were also there, like different type of noise was there. And then model thickness was also greater than the depth of field. So in that condition, we have to take the help of machine learning. So what we did basically, we applied convolutional neural network in image processing. So what we have to do CNN. I will call it CNN throughout. CNN received a great attention in machine learning vision field as it outperformed the state of art image analysis. I have already talked about it. Then, unlike the conventional image processing algorithms, CNN can automatically learn the representative features of object given in labeled image dataset. This advantage allows CNN to deal with the image directly and bypass the complicated feature extraction and feature selection. So students who want to study more about it, they can just memorize this name, and then they can find out many YouTube videos are available, and then they can learn more about it. And programs related to that, like all the codes are also available, those YouTubers, they have given all those things. Or Dr. Dinda is also expert in this, so he can also give you a good idea about it. Because we are running out of time, so I have to move. I cannot explain the diagram here. Now I want to talk about what are the steps of neural network here. So suppose this is the our image, and we have to resolve this image. So firstly, we apply a vertical, we apply some detector, or we can call it vertical edge filter, or we can call it horizontal filter, and we multiply this type of filter with the pixels of image, and we found this image, final image. And this image can be, we can apply a scalar over there. Like suppose this, if this is the zero number, so zero, we can convert that zero uh, into 255, and minus, because zero in this matrix, zero is the maximum and minus four is the minimum. So minus four was, as I told you in the previous image, the minimum value is basically white. So correspond the intensity corresponding to the minimum value is zero, and maximum value is our zero, like 255, and intensity corresponding to the maximum value is 255. And then after that, we apply an activation function on each pixel. Then we can perform max pooling. This is also an operation. Like if you go through this CNN thing, you will find out what is max pooling called. And then we can find out the fully connected layer. And after that, once we have that layer, we will run our simulation, and that will update the filter through back propagation again. And the same process will happen again. So we can apply multiple filters in order to find out a good quality, like a resolved image. While getting image B from image A, we are losing some information. So size of the result matters. So you see here, this is 6 by 6 matrix, and here we have got 4 by 4 matrix. So basically, we have lost some information. So people are using padding in order to in order to not lose the information. Size of the filter will be changed based on the requirement by changing the assigned weights during the training process. This is the example of trainable Veka segmentation, and it is already available in PG. So you don't need to write down any program for the basic CNN application. So again, I would say, because we ran out of time, so you just remember this name. And if you want to, you can see here, we want to summarize. This is the real picture. If you can see, this is the real picture. So these are some veins in this cell. So we want to see where veins are there, where these blue structures are there, and where that gray structures are there. And we can classify and we can train our images, several images, and we can identify. You can see this black one is converted into blue. These veins are converted into red, and the matrix is converted into green. So it is called, this image is segmented. And now we can measure the area of green, red, as well as blue easily through this segmentation. This was the result of our image, but after that we have to perform water shedding also. But this is the segmented image, which we could not achieve with the help of basic image processing technique. Now, learning from today's lecture is process modeling plays an important role in solving quality defects in steel plant. Physical modeling is a robust method to understand the complex metallurgical process. Imaging and image processing are vital parts of physical modeling. Basic image processing may not work if the image quality is poor. And machine learning based image processing is widely used by researchers these days to understand the complex metallurgical process. These are our papers which we published recently, like in last years. So if you want to learn more about the things which I talked about recently in the presentation, you can go through these papers. Thank you. Questions? Thank you very
Thank you,
much.
sir,
So if you, yeah,
for this insightful talk. Now, whoever wants to ask question, please raise your hand. We will unmute you.
yes, please. Who is this? Yeah, yeah. What is the question? Please ask.
Yes, sir. Good morning, sir.
Good, yeah, good morning. Good morning.
So my question, I am working, I am, my research area is in process metallurgy, and my question is, what is the dissolution rate in whenever we are adding more scrap in BOA, the yield rate is less. So how can
Yield
it
rate
be
is less.
possible, sir? How can? Yeah. My research work
Yeah,
is
so
now in process metallurgy.
okay, so it happens like when you add more scrap, like what is the percentage you change? Like from like what is your
Yeah,
current percentage?
13%.
5%? How much? 30,
Yeah,
13%.
13%. Yeah.
Okay. So this is kind of a unusual thing because my experience says that it should not happen like that. Mm.
Is there
So did you?
is there any
Yeah.
relation between dissolution rate of scrap?
Yeah, dissolution is there because your hot metal is basically already liquid. But I would say metallic yield is calculated based on your weight, right? So once you add that weight,
Yeah.
so it is supposed to be melt
Mhm.
down, right? So what will happen,
Yeah.
like if you add more scrap, that's what I'm saying. Like in my
Yeah.
experience, we were
Mhm.
using 5 to 7% scrap, not more than that.
Yeah.
But if you are using
No,
13%,
yeah. Sir,
yeah,
in
tell me.
BOF, whenever in BOF, whenever we are
Yeah.
adding in 10 to 8 to 9%, the scrap
Hmm.
consumption rate, the yield rate is good. That is 90 to 90,
Yeah.
91 to 92%. But whenever the
Right.
scrap is maximized, but the yield
Right.
rate is less.
Yeah, so that's what I was thinking because my experience said that we were adding 5 to 6%. So that time our
Yeah.
yield was very good. So we never encountered such problem because we never increased because we had
Yeah.
a blast furnace, new blast furnace, and we had a lot of hot metal. So yeah, but the thing is that our blast furnace what was quite far from the BOF, right? So the
Yeah.
temperature problem was not that much. So 5 to 6% was
Mm.
enough for us to control the temperature.
Mm.
Yeah, but if you are adding more temperatures, then because it is a solid material, so it will take some time to liquidify. So your processing temperature will increase. Sorry, processing time will increase, and that will increase the amount of slag. And if slag is increased, your yield will go down.
Is there any solution?
Solution like how are you controlling your hot metal temperature?
Yeah, hot metal temperature is quite normal. That is 1350 to 1390
But was it
temperatures.
normal for the normal condition but like I mean to
Yeah.
say it is normal for 9 to 10% scrap, but for 13% scrap it is normal or not? On the other hand, if you do this your endpoint prediction like for carbon, phosphorus, and temperature control in BOF, so that one your blowing practice will also
No,
depend
sir. Sorry,
upon
sir.
that.
Sir.
Yeah.
As per your statement, whenever you adding more scrap, then hot metal
Hmm.
temperature is also more. Then our yield percentage is more. Yeah, I'm correct.
I think so. I think so. But again, like because temperatures are already very high because of oxygen injection, so a lot of
Yeah.
energy is going
Temperature
up.
is not matter, sir. Na?
Yeah, this is yeah. No, I mean to say this is something we have to calculate. Then only we can say anything. What were you saying?
Is there
Come
any
again?
model? Is there any model available for this?
Yeah. There is a model. Like we can control. Like we published a paper last year that is kind of hybrid
Yeah.
model. So you
Yeah.
can go to my ResearchGate profile and you can download a paper. So that paper was published in metals. So we developed a hybrid model. So in that we calculated the scrap dissolution. So formulae and everything is given. You can just make an Excel model based
Yeah.
on that. Yeah.
Okay. Or one
Yes,
more
yes.
question is there any
Yeah.
correlations between the dephosphorylation rate to the FeO and also in carbon or
Yeah.
you
So
say
what
that
happened? Yeah, there is a correlation actually. So if what I remember, because I'm not working in this BOF for a long time, but I can remember
yeah,
that FeO is I think required for dephosphorylation up to
yeah.
15%.
How
But
much
if you
how much
increase,
FeO is, sir,
yeah,
how much FeO is
15% around.
required?
Yeah.
Yeah, no, I'm correct. You are, sir,
Mhm.
you are correct. and that is
Yeah.
15% is required. But is there any relation between how much FU is required to the how much you take the dephosphorizations? Then is there
That's
any
what I'm saying.
correlations?
So that's what I'm saying, because you need certain basicity of the slag. So what happens, like
Yeah.
when you keep on increasing FeO, so it
No,
will
sir,
replace
basicity is
CaO.
constant.
Yeah.
Basicity is constant 3.1 to 3.34 is basicity is almost about to constant. But how
3
much
point.
we will
You are talking about B2 or by B3, or you are talking about B2 or B3?
B2?
B2 is 3 point. No, so what is happening
Yeah.
here, what I understand from the theory, like if you
Yeah.
increase FeO, so what happened, like it will start replacing CaO. And once it is replaced,
Yeah.
so what will
Okay.
happen, basicity will go down. And
Yeah.
if the basicity will go down, then dephosphorylation will be slower. So that is something I think that happens.
So, sir, no,
That's why we
you
cannot keep on increasing FeO.
no, sir, in your lecture you say there is 100 equations are for the dephosphorylation. But one more equation you have
Nine,
given to your
not
researcher.
1900, 99. 99.
Sorry, 99. But you have
Yeah.
give me you have show a one more equation which is helpful for the practical approach.
Yes. Yeah. So that paper, actually, you know what? I believe that these viewer supplier like SMS and
Yeah.
like they can use that equation. And that paper was also published in 2019. And this paper was also published in Metals. So if you go to my ResearchGate profile, you will find out that paper.
Sir,
And all those equations are
sir,
given over there. Yeah, why I'm saying
yeah,
that equation is good, because we could predict the amount of V2O5 and trace element also,
yeah.
like which is very
Sir,
difficult to yeah, which was not
all are
actually given by previous
sir, all
equations.
are
Yeah.
available here using research paper.
Yeah.
All are available,
Yeah.
sir.
So right now, I'm sorry, maybe I'm giving you some wrong answers because I don't remember it. But those things are already available, and you can find out all those things. Like, yeah, if you go to my ResearchGate profile, you will find out.
Because
Okay,
sir, it is most challenges to me.
Sorry to interrupt you both. Okay, so yeah, thank you, Amiy, Dr. Amiy Srivastava, for the lecture, and it's wonderful. And regarding your doubt, Dipti Ranjan, okay, I am sending you the Dr. Amiy Srivastava email ID and his ResearchGate or say Google Scholar link. Okay, you please directly contact with him. Okay, so that will be very good, right?
Okay,
so
sir.
you can directly contact with him and you can discuss whatever problem you are facing. Okay, so is it
Sure.
everything?
Yeah, sure, no problem.
Okay,
Yeah,
sir.
love to, love
We
to.
are running out of time. That's why.
Yeah, no problem. I can connect you with more expert on this area. No problem.
Okay. It's
Okay, sir.
it's
Thank you, sir.
very useful. Yeah. Dipti I will send you all the details of Dr. Amiy Srivastava, right?
Yeah.
Okay, sir. It is pleasure to me.
Okay.
No problem.
Thank you.
No problem.
Thank you, Dr. Amiy, and see you tomorrow at the same time. Okay, for your next
Yeah,
topic.
sure. Have a good one. Yeah.
Okay. Thank
Thank
you.
you guys for bearing with me.
Thank you, sir. Now we are in the second half of the first session. The second talk is given by Professor Salur Srikant Patnaik. Professor Patnaik currently working at Vijay Bhumi University as Assistant Professor, Vijay Bhumi School of Science and Technology. Dr. Patnaik has completed his PhD from NIT Rourkela. During his PhD, he has contributed in the structural dynamics area by considering various complex cell structures for vibration damping analysis. He also presented his research at University of Technology, Sydney in November 2019 and IISc Bangalore in March 2023 in international conference. After PhD, Dr. Patnaik has worked in a government-sponsored project at IIT Delhi in Applied Mechanics Department at Postdoctoral Research Associate. During his research journey, he has published several reputed journal papers and Indian patents. He has worked in 3 different government bodies, DST, MHRD, and DRDO-sponsored project at IIT Delhi and NIT Rourkela. Before this, he has done his MTech in Machine Design Specialization and Bachelor Degree in Mechanical Engineering from SSTC FET and MPCCET Bhilai, Chhattisgarh. He is having more than a decade of teaching and research experience. So now, sir, please.
Yeah, thank you, Arka. Thank you, Professor Dinda, for having me here today. So I think let me share this screen first so that I can go into that presentation which I have prepared. So is my screen visible to all of you?
Yes, sir. Screen visible.
Okay, okay. Okay, so hello everyone. Very good morning to all of you. And really happy to meet all of the NIT RKL scholars, research scholars, and other students. I was there a few years back. So then after that, I went to IIT Madras and IIT